But
So, so do you
anyways,
guys want to do like questions you have about like the existing
I
material,
got you.
or I was gonna do actually a video on the question Kola had about infinities. So
Yeah,
we can
yeah.
do
Do
either
your
way.
thing.
You know.
Sure.
Kickstart the engine.
Yeah, sure. Okay. So,
But
um,
sorry,
We're
we're
being
gonna
recorded,
fuck
right?
with you, right?
hmm?
Right now, we're being recorded.
Yeah,
Testing.
yeah. Is that
One,
okay?
two.
Yeah, that's
Yeah.
very
Yeah,
fine.
okay.
Yes.
Yeah. So, so basically, you had a question about the Infinite Hotel, which is like a video on YouTube, right?
Yeah.
And so it talked about like basically like you have this kind of like bellhop who's in this hotel that has infinitely many rooms, and they're all filled, but then an infinite number of people come up and say, okay, we need rooms, right?
Yeah.
Um, and so it's saying that he can basically clear space by telling the person in room one to go to room 2,
Mhm.
the person in room 2 to go to room 4,
Yep.
the person in room 3 to go to room 6, and then so basically it's like 2, 4, 6, 8, etc. All the even numbers are occupied, but then all the odd numbers are
Yeah.
free, and you can let in infinitely many people again, right? And so this has to do with an idea called like countable infinities, which is something that we'll talk about. It was something invented by Georg Cantor, and so it has to do with this idea of a correspondence between sets. So, for example, when we were talking about functions earlier, right? We were saying that you have functions like, um, let's say I have a set of letters A, B, C, right? And my function maps them to the letters E, F, G, right?
Yeah.
So it does like let's say it corresponds A to G, B to E, C to F, right? And that's what our function does.
Yeah.
Okay. Um, and so what he talked about was this idea of a thing called a one-to-one correspondence, meaning that for each element in this set, there's one element in this set and exactly one element
Oh,
that
so
it
they
goes
share.
to. Yeah,
Okay.
exactly. So the idea is they would have the same amount of elements if there's a one-to-one correspondence. So for example, the number of elements just means the number of things in the set.
Okay.
It's also called a cardinality. So what this is so like how many elements are in this set?
Two.
Three, right?
Oh, yeah.
Yeah,
I was close, but
right. So the cardinality is
Three.
three, and then this one is
Three.
three,
Almost.
right? So let's say I have a set of numbers. Let's say 1, 2, 3, 4, and I have a function that takes them to another set of numbers, 2, 4, 6, 8, like that. Okay, and so there's there's a one-to-one correspondence there because there's a function that basically associates each number
Yeah.
with a unique number, right? In the other set. So if there's this one-to-one correspondence, then it means they have to have the same amount of things in them, right?
Okay.
Are you with me so far?
Yeah.
Yeah.
So with a function like let's say let
A chair.
Yeah.
yeah.
Could have just grabbed one right there.
So if we had this other function where A, B, C goes to D and E, where A and B both get mapped to D and C gets mapped to E, that's no longer a one-to-one correspondence,
They don't
right?
share.
Yeah, because there's not a unique element
Mhm.
that it goes to. So I couldn't like basically start from D and then tell you which one it came from, right?
Like it's not equivalent.
Well, yeah, sort
Yeah.
of. So it's like so basically they don't have the same amount of elements because basically like these two got associated with one thing,
Uh-huh.
right? But if only one thing can be associated with another, then they have the same amount of stuff, right?
Yeah.
Okay. So let's consider the natural numbers. So the natural numbers are 1, 2, 3, 4, and then just sort of going on forever, right? Okay. And now let's consider another set called the even numbers.
2, 4, 6.
2, 4, 6,
No odd numbers.
No odd numbers. So, Cantor basically asks this question, which is bigger?
Even.
So, right, it seems like, or actually more, I think the intuition is more the natural numbers
Yeah,
because there's like
bigger
more of them.
than
It
the
kind of seems like,
odds.
because you have all the even numbers, right? But like,
I mean, you could keep going with even though. To
and
infinity.
you can keep going with the
You
natural
can
numbers
keep going
too.
with natural
Yeah.
numbers too.
So
though.
why they
We're
not
using
tied?
even and odd. So
Yeah.
Mm.
So basically, what Cantor figured out is, okay, what if can I come up with a one-to-one correspondence between these two things?
Mm.
Is there a function that does that? And the answer is yes. If I have the function, which is basically like 2x essentially, where it's saying like I just double everything in this set, right?
Okay. Like squared it.
So 1 maps to 2, 2 maps to 4, 3 maps to 6. Well, just double. 4
Okay.
maps to 8, right? And so I could start from any element in the evens and go and tell you which natural number it came from, right? And similarly for each natural number, I can tell you what element in the evens that it goes to.
half of it or double.
So there's actually a one-to-one correspondence between all the elements in the set, meaning that the sets are actually
So all the way to infinity.
yeah,
There's a one-to-one
correspondence,
correspondence for each number.
between all of them, yeah.
Really? Hold on. I have to think that
You-
even makes.
Yep. For each element in, let's say, the evens, there's one and only one element in the natural numbers that it came from.
Yeah. It's fun. Yeah.
Now I get it.
Yeah.
Because I was asking myself, I was like, how in the world is it a hotel with infinitely many rooms and you
Yeah.
fit infinite
Infinite,
amount
yeah.
of people? Because
That's a
infinite's
good
not a number. It's just like forever.
I
Yeah.
think it's 'cause you
So
think it too much.
how do you then fit more people into something that's already infinite?
Right. I mean, it was just kind of like a thought experiment to think about how big is infinity, right?
Yeah.
And what we find is that the natural numbers and the evens are actually the same size, right?
Okay.
So they both have this cardinality of infinity, which is called Aleph Null.
Olive.
Yeah, Aleph is a Hebrew letter.
I think, yeah. Was it 8? Was it
Hmm?
8? Okay.
So it's the cardinality of countable infinities. So does anyone want to guess what it means that something's a countable infinity?
Infinity.
Countable infinity?
Yeah.
It
So
just
what is the
means that
countable
it's
part?
a number that we can like still count. That's not like so like you can count like 1.999999999 and on. So I guess is that a way of saying countable infinity?
Well, that's actually interesting that you brought that up. So countable infinity is basically like it's literally just like infinities that you can count out, right? 1, 2, 3, 4, 5, 6, all the way up to all the way up to infinity. Well, you can't go up to infinity, but you know what I'm saying.
Yeah.
But I'm saying it's like a countable number, right?
Mm.
And so so then Cantor asks like, okay, so what other things have this same cardinality, Aleph Null, right? So we could look at something like the integers, right? So I know it's a little bit weird that it's labeled Z, right? But the integers is basically like -2, like you come in from negative infinity, -2, -1, 0, 1,
So positive.
2, etc. to like positive infinity, right? And now we know that like Aleph Null is the size of the natural numbers, right? Or the evens, it's the same size, which is the set. Actually, I didn't include 0. I think I did 1, 2, 3, 4, etc. Right? And so then the question is, can I come up with a one-to-one correspondence between the integers and the natural numbers, or is the integers bigger?
I feel like you can. Yeah.
A one-to-one function on them?
Yeah, so some function that basically gives you like a one-to-one mapping between them.
I feel like you can.
Which one is bigger? Can't you?
Well, yeah, sort of. That's kind of the question. Are they bigger? Are they the same size? Is one bigger? Are they the same size?
I mean, if it's negative, of course, anything negative is usually smaller than positive things.
Yeah.
So would you just say that these are smaller than the natural numbers?
So do they have the same amount of elements or not?
I mean,
Question.
yeah. right?
Right. So basically, the
Because it still
one-to-one
has the
function
negative
I could
1, the negative 2, the 0, the 1, and the 2.
yeah. So the one-to-one function I could set up is like this, where basically like every even number, let's say, goes to like the corresponding, like goes to like half of it, and then the odd number kind of goes to like half of it minus, or what is it, like the negative version, the negative half plus one. So if I did like, so for example, like, so wait, three would go to negative one, like five would go to negative two, like that. So basically, I can set up this way that like the evens go to like the positive numbers and the odds go to the negative numbers, right?
Yeah.
I can do that. So are they
Yeah.
the same size?
No. Different size.
Yeah,
They-
I came up with this one-to-one
It will
correspondence.
have to
that
be the same size.
Yeah, it means they're the same size, right? Okay, so the natural numbers and the integers and the evens are all the same size, right?
Mm-hmm.
Okay. Um, and then we could look at something different, like let's say rational numbers. So what do you guys know what rational numbers are?
Rational numbers. Like
I forgot.
dealing
That's
with like
tough.
decimals.
Oh yeah.
Not necessarily
fractions,
decimals.
yeah.
It's basically as long as you have any fraction representation that has that involves integers. So like negative 1/1, and we'd have like 0, and have, let's say 1/. It's a little bit weird to write
Like 2x squared.
fractions this way, but like you can.
Do like 2x squared over 2.
Hmm.
Oh, never mind.
But then you'd be creating a problem.
We don't need variables in this. We're really just talking about numbers right now.
Got it.
And so I don't know if I know the exact function that does it, but there basically is a way to like count all these off, where sort of like 1 goes to 0, 2 goes to 1/1, 3 goes to negative 1/1, and basically you're sort of like writing out all the rationals in a kind of sequence where
What
you're
is it,
saying
like
like
a
a
function?
half, 2/1, then you do like a third, 2/3, and then like 3/1, 3/2, etc.
Oh.
And you could sort of like enumerate the rationals all in that way. And so that means because you can count them, they also are a countable infinity. So, but so then the question is like, is there really anything that's not like a countable infinity, right?
Yeah.
Because it seems like everything we're looking at, it seems like you can count off,
Yeah.
right?
Yeah.
Okay. So then we're going to talk about this thing called the real numbers. So what are real numbers?
1, 2, 3, 1 through infinity. Well,
So
every
it's
real
like
number is
on
from
the-
negative infinity to positive infinity.
No, isn't it like
Right, but so like what values exist in
is it
between
X
there?
value, Y value? I'm tripping.
So like what's different from that and like the integers, let's say?
Like the
One's
whole
fake,
numbers.
one's real.
So the integers are whole numbers for one thing, yeah.
Yeah.
So what's different between them?
Yeah, so like what's a real number I could have that's like not an integer?
Like 0.
2, 0 is
Hmm?
no.
So yeah, 0 is an integer, yeah.
Oh,
Like can you use like
negative 34.
So but that would be an integer still though, wouldn't it?
oh yeah, true.
So because when we're graphing, right, we can plug in certain values that aren't just integers, right? You could what other values could you plug in?
2.
That's an integer.
Ah, okay.
Decimals.
Decimals, right?
Decimals, yeah.
Yeah. So I could plug in, let's say, like 0.5 or like 0.3172689 and sort of going on like that forever. Okay. And then another question is, how are they different from rationals, though? Because rationals, like I could have a rational like a half,
That could give you a decimal.
which is
of
0.5,
Yeah.
right? Which is the same thing. And so you may not know this, but the answer is that there's a certain property to rationals that if you do a decimal representation of it, they always end up having some repeating pattern that goes on forever. So if I try to do a decimal representation of 1/9, it would just be 0.1111111 forever. And you might ask though, okay, so like what about 1/2, right?
Yeah.
Because that like sort of ends. But if you want to think of like ending as being like 0.5000 forever, right? Then it is kind of like it always has this a repeating pattern. And I could come up with, I think a seventh has like a repeating pattern that's like very weird. I think it's like 1 point. I'm gonna be wrong here, but it's like 1.162879530 or something, and that whole thing just like you just keep if you just kept writing it out, it'd be like 162879530, and it would just keep doing that forever.
Okay.
However, I can conceive of a decimal, right, that goes on forever and there's really no repetition to it.
Oh, it doesn't repeat. Yeah. It's
Yeah.
different numbers.
Right? And I could just say, okay, this is going on forever. There's no pattern to it. It doesn't just keep repeating forever.
It's cool.
And that's a real number that's different from the rationals or the integers, right?
Oh, so as long as it doesn't repeat, it's a real number.
Well, though, if it
No.
repeats, it's still a
It's
real
still a
number,
real number.
because a rational is also a real number.
Okay.
But there are real numbers that are not rationals, basically.
Okay.
And so some more common examples that we see of real numbers that aren't rationals are irrational numbers, which are things like the square root of 2.
Square roots.
So if you looked at the square root of 2 on a calculator, you would see that it goes on and there's no, like, there doesn't seem to be any pattern in how the decimal is going.
It doesn't look pleasant.
Yeah, basically. I mean, in a way, yeah.
Yeah.
Yeah. And so there are other real numbers. Does anyone want to guess at some other real numbers?
That
36.
That are the real numbers that
36.
aren't that aren't rationals.
3.5.
3 point.
Well, wouldn't that be
7.
Can we?
if I did 3.5 though? That would basically have that repeating pattern on the end, right?
But 7. There you go. Square root of 7.
And I could also just definitely like represent 3.5 as like 7 over 2, right?
Oh yeah, true.
Yeah.
So 7 would work now.
How about
9.
could you do a number around 3.5?
Okay.
Because like since 3.5 would be 7 over 2, you can find something like in between it.
Okay. So it's like 3
Like
point.
3.6. No, not 3.6. Too close. Or probably something in between, like
Maybe
3.5, like 3.53.
Okay.
3.53.
So if I did that, if I just left it there, or actually it's maybe over 100, right?
That would be 3.5.
So that's irrational still.
Oh yeah.
So keep going.
3.53. 4.
Mhm.
3.
Mhm.
1.
Okay. Stop there.
And then divide that by 100.
Okay.
That wouldn't give you the same thing. Wait.
Would still be irrational because I could
So
still represent it as 3534331 over 10000.
Which should just be 3.53.
Yeah.
Okay.
Right. But keep going. So we have 3.53431
9.
8.
9
Ah.
8
6.
6.
7.
Yeah. And so
Nice.
but if we stopped anywhere, notice that I could give it a rational representation. But if it went on forever
You can't.
and had no patterns, you can't, and that's a real number that's not rational.
Interesting.
And so square root of 2 is like one of those types. There's also other types of there's also other irrational
11.
numbers. How's
11.
how's that irrational?
No, like,
Just throwing numbers out.
So basically, if I'm understanding what it was saying with the video, it's saying there's an infinitely infinite amount of prime numbers.
Yeah, it did say there was
Much.
infinite amount of
Is
prime
this on
numbers, right?
YouTube or something?
Yeah,
Yeah,
yeah.
man, check it out.
So, we can actually get to that in a bit. I just want to sort of like clarify real numbers a little bit more.
Mhm.
So, okay. So, other types of examples of real numbers I could give you
Two.
pi,
Oh, pi.
e.
Oh, what about natural log? Natural.
So the natural log isn't a number.
Oh.
If you ask me for like the natural log of like 2, let's say, that would be
Okay.
square root of
What about theta? No.
10.
They
So
have a
theta's
sine theta
so
or
theta's
no?
a variable.
Oh, okay. That's tough.
I think there are probably some signs like sine. If I did like the sine of, I think pi over 3, right?
Right, pi over pi over
Because that would be the square. Because that would be the square root of 3 over 2.
Okay.
So that would be irrational.
Um.
But basically there are these types of numbers
Mhm.
that are these infinite.
Yeah, that's
Yeah.
cool. That's cool.
Okay, so that's what distinguishes real numbers from, let's say, like natural numbers or rationals,
Mm.
which are all these things we saw before that were like countably infinite, right?
Right.
Mhm.
So now there's this method that Georg Cantor came up with called diagonalization, where I try to sort of like a short like overview is where I try to say, okay, let me try to count off
Mhm.
all the real numbers, right?
Mhm.
Yeah.
Okay.
How does that work out though?
So yeah, exactly. So basically I try to come up with this counting of real numbers, right? Where I say, okay, so the first element of my set is going to be like 1.3572146 and going on. And then the second element of my set is going to be like 2.1350421, etc.
Yeah.
And then 1.68452003 and going on, and then 0.4138. I'm just completely choosing random numbers here. There's no pattern to it.
Okay.
But you don't have. I mean, you could obviously choose something that has a pattern. But what this will show is that if I do this, I can actually find a way to find a another type of real number that doesn't actually belong in here.
Um.
Okay. So what I do is I take the first element of the first number I'm listing, so the 1, right? I take the second decimal of the second number I'm listing, so this 1. I take this the third element of the third decimal, etc. Like that.
Yeah.
Okay. So I have this. So basically, I've constructed this new number, 1.1837, and then sort of like going on forever because I would just be borrowing from other numbers that I listed, right? And that's a real number, right?
Yeah.
So now I can also create a new real number by, like, let's say changing all of these by 1. So instead of 1.1837, I have like 2.2948, etc. Right?
Uh-huh.
Is that okay?
It's
Yeah.
cool.
That makes sense so far.
Yeah. So this is still a real number, right?
Mhm.
But it's a real number that can't be any element in this set.
So it has no elements.
Because, right, if it was this element, then these numbers would be the same, but they're not. I specifically made them so they're not, right?
Mhm.
Yeah.
If these were the same, then this element would be the same, but they're not, right? Because I specifically made it so that they're not.
Yeah.
If this element was the same, these would be the same, but they're not. So it's not in this numeration that I tried to create for the real numbers. So basically I found something, even though I've said that supposedly I could use countable infinities to find the number of elements of real numbers, we've actually found a real number that exists outside of that.
Yeah.
So what this means is, are you guys okay with that idea that this is just a new real number that is not anywhere in here?
It's cool. Cool.
Right. Okay. So then what that means is basically R is not countably infinite, right? And the sort of mind-blowing thing about this is it means that there are some infinities that are bigger than other infinities.
Hmm?
So R is infinite, but it has more elements
Yeah.
than the natural numbers. Isn't that crazy?
It's ridiculous.
And just like
Mind blowing.
So natural numbers are infinitely big, but real numbers are even more infinitely big.
That's crazy.
that just makes my head hurt. Like what?
I know, right? But the whole idea lies in this idea of like one-to-one correspondence. If I can find a function that that there's like one element in the first set for each element in the second set, then they're the same size, and maybe we're okay with like natural numbers being the same size as like even numbers, or natural numbers being the same size as integers, right? That's not a terrible idea, right? Because it's kind of like saying like infinity plus infinity is equal to infinity. We're okay with that, right? Like if you add infinity to infinity, you're still at infinity, basically, right? And then similarly to when there was like in the video when there was like the infinitely many buses of infinitely many people coming up to the hotel, right? It's like saying that okay, infinity times infinity is still infinity, right? And that's okay, and we're all happy, right? That doesn't make your head hurt, right?
No.
It's simple.
Yeah,
It's like 1 times 1.
yeah.
Yeah.
But when we think about like how big are real numbers in comparison to natural numbers, it means that this is actually an infinity that's bigger than your other infinity.
Yeah. But that's enough study for the day.
I keep going.
So I just wanted to
Full tank.
I just wanted to sort of like bring up this new topic, and we can talk about it a little bit more because I like actually talking about these things, and I'm glad that you guys are so interested in like other aspects of it. And obviously I couldn't take up the pre-calc time going over this,
Yeah.
but I think it's a really cool thing, and I want people to have the advantage of, if they're curious about it, to actually like learn about this stuff and try to understand it a little bit.
It's fun.
So if anyone has any questions about that, please email me.
That's crazy. Like, how long would it take for the people? Like, see, this is the weird thing about infinity. You can't say infinity
Can't.
because it's not a number.
Right.
So the people that's infinitely high,
Yeah.
how long does it take them to get down the elevator? Like,
Oh, I
do
see
they
what you're
ever
saying. Yeah,
get
yeah.
Down? 'Cause
If
it's
you
so-
if you tell if you like you're saying like if you tell infinitely people to move rooms, it would take them like infinite
Infinitely
time,
long
yeah,
to-
You
to
would
move.
never get there. That's the whole
Yeah.
point, though. It's like, you know how you said about the asymptote? It
But
never
also-
touches, it keeps going. Like it gets.
Yeah.
Yeah, exactly.
But also, like, let's say, what if each person takes a specific amount of time to get to each room? Then it would only take, in total, that amount of time for them all to move rooms.
Nah.
So
Oh,
like
you're
like
saying
let's say
they'll get
like
there?
let's say it takes someone 2 minutes to move from room to room, right?
Yeah.
And infinitely many people do it. Well, it still takes 2 minutes because it's just a bunch of different people all doing that 2 minute.
But then that's so weird. Like a hotel like that, I knew like it was just like a little like riddle or whatever, or paradox or whatever.
It's like a
they call
thought
it.
experiment, yeah.
But then it's like this. It's like you would basically in that hotel have to move rooms like every 2 minutes.
Right. Yeah,
Because
that'd be
you
very
would constantly
inconvenient.
have
Yeah.
to move
Make
your
room.
room
You never
yeah.
stop.
from infinite people
Right.
coming in and
Yeah,
never
exactly.
stop.
Yeah. I know. Infinity makes your mind hurt, like thinking about
Yeah,
it.
like it's just so like. I wish there was a number we just stopped at.
But
in the world.
but here's the cool thing is
It's the best part about numbers.
like what we can use to basically try to figure out stuff even when there's infinity is this thing called induction. And induction basically just means, and it's a good like general principle to like try when you're stuck on something. It's part of my like math toolkit is basically induction is like start from a simpler case. So right, if we're thinking about like how much time does it take for all the people to move, I just think about, okay, well, how much time does it take for one person to move? And let's say we'll say that it takes like 2 minutes for one person to move, right?
Then that goes for everybody then.
Right, exactly. So then you start from a simpler case, and then you basically need to determine if it applies to bigger cases. And then from there, oops, I misspelled applies to bigger cases. And then from there, I don't really need to do anything else to prove that something, let's say, works for like infinitely many people, because if I said, okay, this worked for one person and it's going to work for all of them, then I'm done.
Yeah.
Right? Like I don't need to prove each individual person is going to take 2 minutes to move if it's a fact that every person takes 2 minutes to move hotel rooms.
Yeah.
And the whole total time for them to move hotel rooms is going to be 2 minutes.
Yeah, the average time.
Yeah.
Okay.
And not infinity.
And not,
Right.
Yeah. But break it down. Yeah.
So this is how we can think about things that are infinitely big,
Uh-huh.
but still like make some kind of sense of it. Is just think about, okay, let's start with like one person or like a simple version, and then does this work for everything?
Yeah.
Right? And so that was actually in a way kind of what Cantor did, right? Like if we talk about one-to-one correspondence between these small sets like 1, 2, 3, 4, 5, 6, right? We can think about, okay, well, if we can come up with some function that maps it one-to-one, they're the same size, right?
Yeah.
That's an easy principle to understand when we're talking about things with like finitely many. But then he used it to extend it to thinking about things that are infinitely many, and came up with this idea that, okay, there's a certain size that's countably infinite, and then there's a certain size, which is the size of the real numbers, that's uncountably infinite.
Okay.
Because remember, previously, when I tried counting it, right, I could come up with a new number that's not in
Every time.
not in the set. Yeah.
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 Okay.
I could come up with, in fact, infinitely many new numbers that
Yeah.
don't belong in that set.
Different combinations.
Yeah. Mm-hmm.
Okay.
That's crazy.
Yeah. So okay. So I think that's something to think about for a little bit, and then